This video will talk about how to parameterize how to parameterize an ellipsoid in n-dimensional or the Euclidean space. We would like to extend the equation or the parameterized equation of an ellipsoid. What we have seen before in high school, okay, if you have an ellipsoid graph, okay, the equation of an ellipsoid would be something like this, right? Equals 1. So that you know that an ellipsoid is basically like you have a circle and you kind of press it into dimensions so that the width of the two axes are not the same. Here, because of this parameterization, the width of the principal axis in X would be 2a, right? And here the coordinate, it would be minus b and b. From this parameterization, it's not actually hard at all to to extend this parameterization in n-dimensional. So first of all, I would like to switch the use of the variable x and y, because this is just in R2. I would like to go beyond that. So let's change the notation into x1 and x2. In an ellipsoid equation, you must notice that it's very intentional to make the denominator here a non-negative. Okay, otherwise it's not an ellipsoid. Okay. Now from this parameterization, now let's let's rearrange it into kind of make it more similar to a vector format. So this is quadratic function in x1 and x2. So how about write it in a vector format? You say this is a row vector x1 and x2 multiply with this guy. Okay. Then you also see that this is 1 over a square, 1 over b square. How about look at this as the inverse? Okay. Now, I try to extend it to a vector case. Okay. Now you see that the row here, the intention of using a square and b square so that these entries are non-negative. And because it's in the denominator, it's actually correspond to the inverse operation here. So let me state from here, you will see that this is an ellipsoid in R2 that you have learned from high school. The statement of an ellipsoid in n-dimensional space is the following. It is a set of x of vector x in Rn such that x minus xc, the center, transpose P inverse x minus xc less than alpha, where P is a positive semi-definite matrix. So you see the extension here. Instead of originally that, the simple case, okay, this is the matrix 2 by 2. And the reason why that is a square and b square, so that this matrix is positive semi-definite. Now we extend it into n by n. And the positive property here is actually the condition of P. P has to be symmetric. P has to be positive semi-definite. But now in n-dimensional, P allows to be any symmetric with the positive property. But P doesn't have to be restricted to a diagonal only. And of course, the translation term here, you know that it only affects the center of an ellipsoid. Xc is also a vector in Rn. Okay, so this notation, this is a set. Okay, and of course, if you draw an ellipsoid, if you change this guy to inequality, it basically means the area in the ellipsoid. Okay. So I would like to after. Okay, let me just put the notation here again. The way that we parameterize the ellipsoid is this. So ellipsoid is parameterized by the center, the matrix P, and the level. Alpha will tell you how big is an ellipsoid. Of course, if lambda is 10, the ellipsoid is this. If alpha is 500, you will see that it's going to be bigger, gradually bigger. Okay. Now, in this video, I would like to basically give a basic step of how can you sketch an ellipsoid in Rn, and we're gonna see its application. We use the ellipsoid a lot of times because parameterization of an ellipsoid. Parameterization of an ellipsoid is basically a quadratic form, a quadratic function in X, and the quadratic form in X has a lot of applications in engineering. One of the application is the concept of Gaussian vector that we will talk about it shortly after we see how to sketch an ellipsoid. Okay, first, now, how can you how can you sketch the shape of ellipsoid? Is it going to be this? Is it going to be like American football, the rugby, or it's going to be rotated this way? How do we know? How do we know that ellipsoid where, and how does it look like in n-dimensional? Okay. Now we're going to explore a lot of the result from matrix analysis, especially eigenvalue decomposition. Now, everyone agree that if we would like to sketch this area, it's going to be the same thing as, it's not hard. If we can sketch this, of course, we can sketch ellipsoid. All right, this is an equation. Equation is going to be the point along the ellipsoid. If we change it into inequality, it's going to be area and in the ellipsoid. And of course, if you have XC, you know that you just translate, right? If XC is 1, 2, you just move this ellipsoid to have the center at 1, 2. So it's not hard. The translation and the inequality thing is not are not difficult to generalize. So basically, I want to see how these equations can be sketched on Rn. Now, as I mentioned, that the matrix P has to be positive semi-definite. Has to be positive definite. Otherwise, it's not called an ellipsoid. Just like what we see here, the denominator here has to be positive. So it extends to the fact that P has to be positive. Okay. When P is positive definite, it means that P also symmetric. And that means P has an eigenvalue decomposition like this. And as we have seen several times in the analysis, that U is unitary matrix. The columns of U are orthogonal because P is symmetric. Okay, so how about P inverse? P inverse is not actually difficult to obtain because of the orthogonality in the columns of U, because then you can prove that P inverse is given by U D inverse U transpose. If you want to prove very simple, you just multiply these claim to be in the inverse with P, and you see that it becomes identity matrix. Okay. Of course, the inverse exists because the eigenvalues of P are all positive from the assumption. From the assumption that P is positive semi-definite, all the eigenvalues are positive. Not only, I mean, strictly greater than 0. Okay. Now we're going to plug this term into the equation of x. Okay. Now let's see this equation. How about if we take a look at this as a new vector y? Of course, you're going to have y transpose d inverse. Okay. And if you just expand, if you just expand the quadratic term, you will see that it is actually y1 square lambda 1 plus y2 square lambda 2 dot 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 yn square lambda n equals to alpha. Then instead of writing sketching the set of x, how about we sketch the set of y first. Now it's not actually, that is not hard, right? Because from this equation you know that how to sketch it. Y1, okay? So for y1, when y2 is 0, y1 is going to be square root of alpha lambda 1. For y2, it's going to be square root of alpha lambda 2. Okay? Then, or you can look at this way. You can also look at this parameterization. I can also write this as x transpose u d minus 1/2 d minus 1/2 u transpose x equals to alpha. I can just, it's just the same way that we talked about in the previous lecture about diagonalization of you know of a positive definite. Then I call this guy Z. Of course, this guy is Z transpose. And everyone knows that if you are to get sketch Z transpose Z equal alpha, Z1 square plus Z2 square dot 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 Zn square. Everyone should know that, oh, this is just this must be a unit norm, not a unit, sorry. This is just a norm ball, a circle, a ball in the n dimension. Okay, so the first step here, we would like to sketch an ellipsoid, which is parameterized in some variable x. But we know that if we just expand a little bit about the decomposition in P, we get the equation in variable y, or it could be a variable of z that can be sketched in Rn more easily. Okay. Now let's take a look. Let me explore the option here. If I can sketch, so the set of y is if you look at this, okay, it looks like a circle that now you have different width in both principal axes. Put more after. Okay. Now, from the previous result, okay, if you take a look at y equal u transpose x, it means x equals uy. You use the inverse of u transpose, which is just u. Okay, now you want to sketch the set in x. So I would like you to take a look at the principal axis of the set of y. Set of y is like an ellipsoid that is not rotated yet. Okay, so the principal axis of the ellipsoid in y is actually the standard unit vector e1, and here is the standard unit vector e2. What is e1? E1 is 1, 0, e2 is 0 and 1. So to go back to x, we use this relation that we just derived, x equals to uy. So basically all the vector, now I'm going to use another color. When I point out these arrows, it means all the vectors that I'm drawing right now is actually the vectors on the ellipsoid. This is a vector y. So if you want to sketch the ellipsoid in X, you basically map all the green vectors by this transformation, uy. What do we know about uy? Okay, so this is E1 in E2, this is Y1 and Y2. When you map, okay, now we can also map only the principal axis of the ellipsoid in Y. So if you map with E1, U has many columns. Let's say it has n column. If you multiply with E1, which is 1, 0, 0, 0, you're gonna get U1. If you map with E2, the second principal axis of the ellipsoid in Y, you're gonna get again U1, U2, dot dot dot, UN, 0, 1, 0, 0. And then you're gonna get U2. And so on. So that means, oh, one more thing. You know that U is unitary matrix. So what we have seen before from the matrix analysis is that one main property of the matrix transformation with the unitary matrix is that the norm of X is going to be, will not change. The norm of X is going to be the same as the norm of Y. So the figure that I sketched before, that the green vector are actually all the vector that lies at the ellipsoid of Y. So if you make a map, so you're gonna map all the green vector with U. The result of the mapping will simply change only the direction, but it will not change the magnitude or the norm. Okay, so the result of the ellipsoid in X is going to be that. So first you map E1, you map with E1, so you get U2. Let's suppose U1. Suppose the first eigenvector has this direction. Okay, and because all the columns of U are orthogonal, so U2 must be perpendicular to U1. So let's just say U2 is this. Okay, then finally you can just sketch that this is the red one is the ellipsoid in the variable X that you want. The parameter of the ellipsoid, the width, the principal axis, the width here would be, I mean the width of this part would be square root of alpha lambda 1. This part would be square root of alpha lambda 2. The width of this guy is going to be the same as this. It will not change. It will only change in the direction. The ellipsoid, the red ellipsoid, which is the ellipsoid in the variable X that we want, would be just the rotated version of the ellipsoid in the variable Y. Okay. So this is it. This is how we plot an ellipsoid. So let me illustrate with with some plot in MATLAB. Okay. So how about my P is 1? Of course, my P is 1, 2, 0, 0, 4. Okay. If I plot, this is just some function that I write it myself. Okay, plot ellipsoid. Okay, center at 0. Okay, alpha is 1. Okay, now let's see. You will see that this is an ellipsoid with the principal axis on as a standard unit vector. Okay, and the width and the width of the ellipsoid is going to be, because okay, here my P, okay, is already a diagonal matrix. Okay, so you immediately know that the eigenvalues of P is 2 and 4. So the width of this guy, the width of this guy would be square root of 2 and square root of 4, which is 2. And you see exactly on the graph here. So this portion, the principal axis on the x1 direction, the width is supposed to be the square root of alpha lambda 1, which is alpha is 1, lambda 1 is square root of 2. Okay, if I change a little bit, I need to come up. I need to put an example P, of P that my P has to be positive semi-definite. Okay, in this example, so I run the command again. Now you see that here my ellipsoid is going to be a rotating version. Okay, now let's verify the parameter of this ellipsoid. First of all, the principal axis of the ellipsoid has to be in the direction of what? Of the eigenvectors of P. Okay, this is the result U. Okay, U, the first column is minus 0.5 and 0.3. The second eigenvector is 0.3 and 0.9. Now let's take a look at the plot. So if we look at the first principal axis, do you see the mouse? Okay, it seems like the mouse is not appearing on the screen. Let me move a little bit. That means what I'm talking is the principal axis. So the principal axis, the first principal axis, is supposed to be in the direction of U1. So you see the value minus 0.9 and 0.3. Okay, makes sense, because let's just verify with the direction. And the second principal axis is supposed to be a vector. Supposed to be in the direction of the vector 0.3 and 0.9. 0.3 and 0.9. It's not. Hold on. Oh, it's the other way around. Sorry. Now let's change again. P1 and P2. Oh, okay. You need to. So, from the eigenvalue command, all right. Now we have to take a look at the width of the ellipsoid as well. If you look at the first eigenvalue, it is 1.5, right? 1.5. So this is a smaller eigenvalue. Okay. If you look at the axis that has the shortest width, is supposed to be this direction. Okay, this direction. You see the mouse that I'm moving? Okay, and you see the vector that represent this principal axis that correspond to the width of, square root of 1.5. That vector is minus 0.5 and 0.3. See, so the vector is actually lying in the second quadrant. On the other hand, the second eigenvalue is 4, is the one that is bigger. Okay, so it corresponds to this axis, this principal axis. And the direction of this principal axis can be represented by the vector 0.3 0.9. So this is a vector that is lying on the first quadrant. Okay. So here you have seen how to sketch an ellipsoid in Rn. Next, I would like to come back to our screen. I would like to talk about some information. Some application on the ellipsoid. When do we see an ellipsoid? Okay, I'm gonna just erase it. One of the application is actually the concept of Gaussian vector. The Gaussian vectors, if x is a random vector that has n component, and if x has a normal distribution of Gaussian parameterized by sigma, which is covariant metric, and of course this sigma is positive definite, then the the joint PDF of x is this. So we're gonna learn about this as well when we talk about a Gaussian vector. But let me just give you the result, the main result. Okay, this is the PDF of the Gaussian vector, and you see that what's so special about Gaussian vector is that the form of the PDF falls into an exponential function. Not only an exponential function, but its exponent is a negative quadratic form in X. This is the main feature of Gaussian vector. And now you see how it appears, that kind of, the form, the quadratic form that is similar to the parameterization of an ellipsoid. Okay, now the connection is the following. Okay. It can be explained that if you generate x according to this normal distribution, if you just put a bunch of just generate a bunch of realizations, we can show that those realizations will lie on the n-dimensional space in the shape of an ellipsoid. For example, if my sigma is if my sigma is, let's see, if my sigma is 1 minus 1 and 2, okay, I know that what I'm talking about here is two-dimensional Gaussian vector. X1 and X2 has correlation, which is -1. So you can expect that if you make a scatter plot, it should be that when X1 is big, X2 should be small, something like this. And variance of X1 is 1, variance of X2 is 2. So the range of X2 should be bigger than X1. Okay. Now, now, one simple way to support this idea that if you make a scatter plot of Gaussian vector, its shape would lie into an ellipsoid shape in Rn. Now, you take a look at this equation. This is just like an ellipsoid. And now I'm going to do the same thing. I'm going to perform eigenvalue decomposition in sigma. So it's going to be U transpose. Okay, and of course, sigma inverse is UD inverse U transpose. So we go the same way. We just derive everything the same way as before. I also factorize the inverse of d into d minus 1/2, d minus 1/2. And now I call this guy z transpose and z. You check the dimension. X is a vector. X is a vector. U is matrix. D minus 1/2 is a matrix. So matrix vector, it becomes a vector. Okay. And again, if we, of course, z transpose z is going to be z1 square plus z2 square dot 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 zn square. And what we know from this transformation, z is d minus 1/2 u transpose x. Okay. So what do we know about z? What do we know about the covariance of z? Of course, you should be able to verify that the covariance of z is I, because this is the transformation that we have discussed before, the affine transformation that decorrelate x and also normalize the variance of x. So if the covariance of z is identity, it means that all the entries of zi are all uncorrelated, and the variance of zi is also 1. Okay. Now, what do you know about these quantity? Z transpose Z. Okay. So if we talk about if I now let me sketch here. So from the statistics, X is Gaussian. Okay. We're going to learn from the property of Gaussian vector. If X is Gaussian, if X is transformed by an affine transformation, the resulting vector is also Gaussian. Okay, it's also Gaussian. But here, Z is a Gaussian that has a unit covariant matrix. Okay. Now, if Z is is a Gaussian vector that has unit covariance, of course, if you make a scatter plot, of Z, it would look like a circle, because all these ZK are completely uncorrelated. Okay. Now we're gonna talk more. About the bound of this guy, like the radius of the circle. Okay. Now, if I examine this property, if I would like to compute the probability that my Z transpose Z is less than alpha. Okay. I would like to see, what would be the percentage that coverage, my scatter plot if I determine this radius. Or on the other hand, I can also come up with a question that if I want to cover this scatter plot with the probability of alpha, not alpha, with the probability of 0.9, for example, what would be the radius of that coverage? Okay. Now, let's just say that, okay, if I want to cover this scatter plot of Z, if I want to guarantee it with the probability of 0.9, can we determine this alpha? Okay, and of course, in order to, if we can determine alpha is going to be the radius, right? Because this is Z transpose C less than alpha. if you look it as a set of Z, this is just a circle. This is normal in n-dimensional space. So knowing alpha, or not radius, it has to be the square root of alpha. That has to be the the radius. But basically the same thing. You know alpha, you know the radius. Okay. So the question is, if I give you the probability of the coverage, okay, can you determine the radius of the circle that is guaranteed to cover, about 90% of the points in the scatter plot? Now we're going to use the property that we have just said. Okay, X is Gaussian, Z is also Gaussian. This is not like very immediate result, not trivial. I mean, you need to see the proof when we talk about the Gaussian vector. But I just state the final result here. If Z is Gaussian, but because Z is uncorrelated Gaussian with variance of 1, then also it also comes with the property of Gaussian that uncorrelated Gaussian are also independent. Okay, this is another property that you're gonna learn shortly after we have another video or discuss about this result. But I hope you can recall some simple fact in statistics that when you have independent Gaussian, do you see the screen? Z1 and Z2, the component Z1 and Z2, the dot Zn are completely independent Gaussians. So the sum squared of independent Gaussian is chi-square. So what you're deriving here is actually the probability of the chi-square variable with n degree of freedom, because you have n terms here. Okay, that is, you like to find the probability of a chi-square variable with degree of freedom n less than alpha, and that probability is 0.9. Of course, how can you determine alpha? You take the inverse of the CDF of chi-square distribution. Okay, now let's illustrate this result. Okay, I'm gonna go back to MATLAB again. Okay. Okay. So I'm gonna put this is a covariant matrix C that's supposed to be, covariance of Gaussian. Okay. So in this code, I generate X, which is supposed to be Gaussian with that Gaussian parameterized by the covariant matrix C. Okay. If I make a scatter plot of X, okay. I remove. If I make a scatter plot of X, it looks like this. Again, confirm with the parameter. Covariant of C is 1 minus 1 minus 1 and 1 and 2. Variance of X1 is 1. Okay. Variance of X2 is 2. X1 and X2 are correlated with the minus sign. Okay. So again, you can also confirm the shape of an ellipsoid with what? With the eigenvector of C and the eigenvalue of C. So first, the first principal axis, has, the width of that principal axis is supposed to be the square root of 0.3. Okay, let me just compute. Okay, so it's supposed to be 0.6. So let me kind of stretch the line that's supposed to be the principal axis. Okay, so the first principal axis has the width around 0.6, so it's supposed to be this direction. So in that direction, it's supposed to be a vector in the direction of minus 0.8, minus 0.5. Okay. Secondly, the second principal axis has the width of 0.6, 1.6. So it's this. Supposed to be this. Okay. And the direction is in the vector in the second quadrant is minus 0.5, 0.8. Now I'm going to plot an ellipsoid overlay on this scatter plot. First, I'm going to use the alpha equals to 1. So it's this ellipsoid. Okay. Now I would like to draw an ellipsoid that guarantees to cover 90% of the points in this realization. As we have seen before in the analysis, maybe you scroll back to the video about a few minutes ago. To derive that alpha is supposed to be the inverse CDF of chi-square distribution with the input argument as the value of probability, which is 0.9, and 2 degree of freedom. So alpha is 4.6. So if I plot the ellipsoid corresponding to that alpha, okay. So this is the second ellipsoid. Okay, that alpha is about 4.6. How many minutes have we? Okay. So in this video, we have captured about how to sketch an ellipsoid in n-dimensional. The key word is that you perform an eigenvalue decomposition on the matrix P that parametrize the ellipsoid. Okay. Once you know the ellipsoid, one application is that because the contour of the PDF of Gaussian distribution is a quadratic function. So it closely relates to the concept of ellipsoid. Another concept is that we can also draw an ellipsoid that cover a certain probability of points of Gaussian realizations on the n-dimensional, and use the relation of the sum square of independent Gaussian is a chi-square. So and that would be all for the lecture in this video. The concept of ellipsoid will be used a lot again in another class of mine, especially in optimization. There will be a lot of engineering optimization problem will encounter quadratic function. Again, it will relate to ellipsoid concept here. Okay, so let's stop now.